Hello, I'm your host, Dr. David Urban, and I will be guiding you through Brown and Poon's Introduction to Organic Chemistry, 6th edition. The slides were downloaded from the Wiley Instructor Companion site and are copyrighted by Wiley. The commentary is my own. I have divided each chapter into smaller sections to make it easier to view on a wide variety of platforms. So let's begin. We will continue with Chapter 2, Part 2, Acids and Bases. So as we learned before, when we had that Bronsted-Lowry acid and bases, we have an idea of a scale of strong acids versus strong bases, strong acids and weak bases. And so let's go a little bit more about what strong acids are and what kind of influences them to be strong acids or weak acids, okay? The classical definition is a strong acid, one that completely or almost completely dissociates in water to form hydronium ion and its conjugate base, okay? For a strong base, it's the one that almost completely or completely reacts with water to form hydronium ions, okay? So most commonly, our strong acids are things like HCl, HBr, HI, nitric acid, sulfuric acid, and perchloric acid. Okay. Now, our strong bases tend to be those metal salts like lithium hydroxide, sodium hydroxide, potassium hydroxide. Okay. These are what we consider the very strong acids and strong bases because they almost completely dissolve and almost completely dissociate. Okay. Now, the other things, and especially in organic systems, in organic systems, most of the time we have what are called weak acids or weak bases. And these are things that are only partially dissociated in water to form hydronium ions. What that means is they have some equilibrium between being their fully acidic component and their conjugate base. And so we will see in those reactions is we'll see this equilibrium symbol here. And the way in which that is shifted tells you which side the equilibrium lies on. For example, the smaller side of this is shifted to the acetate ion, and the bigger component is actually to the acetic acid. So it's saying when we dissolve acetic acid in water, a lot of it is its entirely acidic component, only some of it has dissociated to form the acetate ion, okay? This is also true for weak bases. Weak bases only partially ionize or dissociate in water to form that. One good example of that is ammonia. Ammonia here can accept protons. So water is actually the acid in this situation and donates a proton to this to create the base. When it does so, it creates the hydroxide ion. And again, the equilibrium is shifted toward ammonia dissolved in water, with only a little bit of it being the ammonium cation and the hydroxide anion. Okay, so that means that when we have acid-base reactions, we have different things that will change that equilibrium. And that equilibrium means that we have a different concentration of the acid by itself and its conjugate acid, or the base by itself, or the conjugate base. Okay, so if we think about acetic acid dissolving in water, we know we have an equilibrium here. And in that equilibrium, we have, this is our acid and this is our base. And when we dissociate it to form a hydronium ion here, this base right here is actually a stronger base than water is. It is more likely to accept a proton than water was. Now, the hydronium ion is actually a stronger acid than this was, so it's more likely to give away its proton than it has. That means that because the product form is actually a stronger acid and or stronger base than the two starting materials, the equilibrium is shifted toward the neutral species. Okay, so if we looked at an equation on how we would figure that out, we would want to figure out what the acidity constant of this would be by measuring the concentration of the hydronium ion times the concentration of the conjugate base over the concentration of the original acid. And we don't include the concentration of water there because that, in assuming we've dissolved it in water, that concentration of water is just removed from the equation, okay? When we do that, what we can see is we end up getting a scale of how strong or weak that material is. So if the constant lies way on the side of the starting materials, we're going to get a larger and larger number, okay? And typically, when we do that, we're going to take the log of this acidity constant here, and that way we get what we call the pKa, or the log of the acidity constant of the material. So if we compare the acidity constants of different materials and look at them in that scale of acids and of organic materials and acids here, we see that a very high number here means it's a very, very weak base, okay? A weak acid, sorry, weak acid. So that means ethane itself it takes a lot to get that hydrogen to disassociate from that carbon-hydrogen bond to protonate something, okay? Which means it's almost all shifted over here. A very large number means it's almost all the molecular acid form, okay? So as we move down the scale here, we see the equilibrium, the constant, the log of the acidity constant going down, okay? When the log of the acidity constant goes down, that means it's becoming a stronger and stronger acid, okay? Once we get down to what we call the strong acids here, right here, notice those values are negative, okay? So that means that there's, you know, that of the log of 1 gets you down to your negative numbers. And so these are almost completely shifted from the acid to their conjugate bases when the numbers get negative here. So if we notice here, this is where all of our strong acids are, our sulfuric, our HCl, and our bromine. So once our numbers are really, really small or negative here, that means they're really, really strong acids, okay? Now, remember when we, in the previous slides, we showed you that strong acids are very weak bases, okay? Make very weak conjugate bases. Okay, so that means these strong acids have very weak conjugate bases. That means that water and hydrogen sulfide and chloride and bromine and iodine here are very weakly basic, okay? They're not strong bases. They are not going to try to take a proton away from something, okay? But notice that the conjugate bases of these things are starting to get stronger and stronger, okay? Which means very weak acids make very strong bases. So once we get up to things where we start pulling that hydrogen off ethylene here, that anion there really wants to steal protons away from everything else below it, okay? Think about anything up here is going to steal a proton from anything down here, okay? Because, or anything over here, because it does not want to be the base, it wants to be the neutral molecule. So you can think of every weak acid is going to be a really, really strong base. And the relative scale of this is going to tell us which way a reaction is going to go. If your base is up here, it's going to react with something below it on the list. If your base is here, it's going to react with something below it on the list. We're going to see this happen time and time again when we look at our reactivities. Okay. So how do we determine the position of our equilibrium right here? First thing we want to do is we want to identify what the acids are in the equilibrium. Remember, there's going to be one acid on the starting material side and one acid on the base side, okay, of the equation, okay? So you can think about this is the conjugate acid. We're going to compare the conjugate acid strength to the acid strength and look at which one is stronger. So we're going to figure out which one of those is on there. And then we're going to use the information on table 2 to decide which is the stronger or weaker acid. Okay, remember, a stronger acid always gives the weaker conjugate base, but a weaker acid always gives a stronger conjugate base. So we want to just look at the acids and look at that acid strength. So the stronger acid will always react with the stronger base to give the weaker acid, okay? That means the equilibrium will lie on the side with the weaker acid. So we only need to identify the acid on each side of the equation, okay? So let's look at this. So we don't care about how strong the bases are. All we care about is what is the acid on each side of the equation first, okay? So on this side right here, we look at this, and this right here is the one that's going to give away the proton. That means it's the acid, okay? This is going to accept the proton, making it the base. We're not going to worry about that. On this side here, this was the acid, so it is now the base. So it's willing to accept a proton, so we're not going to worry about that. But the ammonium right here is now the acid, okay? So we have, this is now identified as the acid on this side of the equation. This is now the acid on this side of the equation. And by comparing the pKa values, we'll see which direction it lies, okay? So our pKa value here is 4.7, and our pKa value here is 9.24. Okay, we're not looking at absolute value. We're looking the one closest to a negative number, the one closest to 0, is the one that's the strongest acid. Remember, our pKa value goes from very high on very weak acids to very low to negative numbers on very strong acids. So this 4.76 is less than 9.24, meaning this is the stronger acid, meaning that the equilibrium is going to lie in the direction of the weaker acid. Okay, so let's get that set in our head. The lower the number, the stronger the acid. The thing that's the weaker acid, the equilibrium is going to lie in the direction of the weaker acid. Okay, so what influences whether something is more or less acidic? Okay, so there's 4 factors to consider when we're looking at how acidic something is going to be. Okay, and so having these 4 things in our minds will help us decide if things are going to be higher or lower acidity if they're similar compounds. So the first thing we have to do is look at the electronegativity of the atom bonded to hydrogen. The more polar that hydrogen bond to that other atom, the more acidic it's going to be. We have to look at, is there resonance stabilization? Can we draw that anion in one or over multiple atoms? If we can take that anion over multiple atoms, the resonance structure will give us stability. Then there's an inductive effect, and the inductive effect is things that are attached to the atom that the hydrogen is bonded to can pull electron density away from that atom, making it change its acidity. And then we also have to look at the size and delocalization of the charge, okay? So as ions get bigger and bigger, it's easy to localize that charge or delocalize that charge over a larger material, changing our acidity of our system. All right, let's look at each of those individually and how they affect our acidity, okay? So just looking at electronegativity right here, if we look at the electronegativity of carbon, it's about 2.5. Nitrogen is 3, oxygen is 3.5, and fluorine is 4. Remember, that's our highest electronegative atom right here. And as such, as the electronegativity increases, the acid strength increases, okay? So that's one of the 4 factors. So electronegativity, so acidity increases as our electronegativity increases, okay? Okay, our second factor is resonance. Remember, when we drew the resonance structure of the carbonate, the acetate ion, we could have that oxygen on one oxygen habit and then draw this the electrons moving to the other oxygen. So we can have part of the charge on one oxygen and part of the charge on the other oxygen. So by resonance structure, we can move that charge around, okay? If we can move that charge around, that means that that anion form is going to be more stable. And that means that if we can stabilize that charge over more elements, it's going to be more acidic, okay? So by just comparing the oxygen here and the oxygen here, on the carboxylic acid, we have a hydrogen bonded to oxygen. On this alcohol, we have hydrogen bonded to oxygen. So just by electronegativity, they should be the same acidity. However, because we can delocalize that charge over two oxygens in the carboxylate ion and only the one oxygen in this alcohol ion, that means that the proton on the carboxylic acid is more acidic. Notice it has a lower value, it's 4.76 pKa. This is the higher value, making it the weaker acid of almost 10 points higher. So that means that the carboxylate ion is more acidic than the alkoxide ion here, even though the hydrogen is bonded to the exact same atom. And it's all because of the resonance delocalization on the charge. Okay, so let's show that again. Remember when we drew our resonance structures for our acetic acid here, we had to take away the proton first. When we take away the proton, that gives us our charge right here, which means we can move these electrons in and these electrons out, meaning we have a resonance structure here, where that charge can be here or here. By having that be charged there or there, we get higher stability and therefore more acidity. If we try to draw a resonance structure on this alcohol structure, when we look at our Lewis dot structure, there's nowhere for these electrons to go. If the electrons went in here, we'd have to break a bond over here. That doesn't follow resonance rules, and therefore that ion, this anion has to stay there, making it less acidic because it cannot disperse that charge. Okay. So the next effect we have is what we call the inductive effect. And what the inductive effect is that we're not changing the electronegativity of this atom here. This atom here, this carbon atom, we're not changing its electronegativity. However, we have things that are bonded to it that can pull electron density away. Okay, so the atom itself is not changing its electronegativity, but it's having some of its electron density pulled through the bonds to the more electronegative atoms it's bonded to. So if you can think about it, it's not a direct effect because it's not directly bonded to that oxygen. It's an indirect effect or inductive effect because it's bonded next to or an atom or two over from there. And that means the closer those electronegative atoms are to that species, the more it will affect the acidity. So if that's true, that means that the carboxylic acid here with 3 hydrogens on it is going to be less acidic than the ones with these 3 fluorines on it. This is going to be more acidic because it's pouring more of the electron density away from this anion. And if we look at the pKa value, we have a pKa value of 4.78. Remember, the closer we get to 0, the more acidic it is. The pKa of the trifluoroacetic acid is almost 0, 0.23. So just having those 3 fluorines on there has dropped the pKa or increased the acidity of the thing just through induction. Okay, so the other way we can do this is by size. Okay, remember, fluorine is the most electronegative atom, so that's part of the rule, is up and over here. But now the acidity within the HCl, HBr, HF, and HI is controlled by the size of the ion. Okay, iodine ion is the biggest anion of the set and therefore is actually the most acidic of the set, followed by bromine and chlorine, and then fluorine is the least acidic in that series. Now, fluorine is the most electronegative, but that's not the only thing we have to look for. Fluorine is much smaller than the chloride ion, which is much smaller than the bromide ion, which is much smaller than the iodine. Therefore, iodine is the most acidic, even though fluorine is the more electronegative. Okay, so we have to think about all four of these rules when we think about acidity and its effect. Okay, and this is further explanation that because the iodine is the largest atomic radius, it has and distribute that charge out over a larger area, and by distributing that charge out of a larger area, it is the strongest set it's the strongest acid. So it's a combination of those four rules: electronegativity, the atom it's bonded to, resonance delocalization, the inductive effect, and the size of the ion that create the acidity of the compound.